Alright, this video is on the calculation of energy based on a wavelength of light. Okay? So, first thing we need to have is the equation, which is energy is equal to Planck's constant times the speed of light divided by wavelength. Okay? Now, a couple important facts you need to know is what these variables are. So, obviously, E is equal to energy. Okay? Okay, h is Planck's constant, c is the speed of light, and lambda is wavelength. Okay, so one thing that we need to know is the value for all of these, because obviously I have four variables here. I need three of them to solve for the fourth. Okay, now which variables you're going to have to solve for are either going to be the wavelength or the energy. Okay, so if you were to have two questions on a test involving this equation, you're probably going to have to solve for each of them. Okay, so let's go ahead and take a look at the wavelength. The wavelength is going to be with one of two units given in the problem, but whenever you're using this equation, it needs to be in meters. Now, unfortunately, the problems that I'm giving you are the wavelength is going to be in nanometers. Okay, a nanometer is a billionth of a meter, which means that 1 times 10 to the 9th nanometers is equal to 1 meter. You will need to do dimensional analysis to convert the nanometer value into meters when using this equation. Okay? Energy, its unit is going to be joules, okay, capital J. Now, the constants up here, the nice thing about them both being constant is the product of them are also constant. Okay, and I'll go ahead and solve for that real quick. Okay, let's go back this way. H is Planck's constant. It is equal to 6.63 times 10 to the negative 34 joule seconds. Okay, and the speed of light, C, is equal to 3.00 times 10 to the 8th meters per second. So if I was to multiply those two numbers together, right, so here's a little practice in using scientific notation for multiplication, but remember you also need to apply your sig figs. In both cases, however, they have 3 sig figs. Okay, so if I was to multiply a unit with joules seconds, and I multiply that, which kind of is the same thing as saying it's over 1, right? And I divide that or multiply that by meters per second, right? You'll notice that my seconds will cancel out, and I'm left with a unit of joules meters. Okay? Now, this becomes important that this value or this unit is in meters because that's, again, why you wanted to convert your wavelength into meters. So when I multiply 6.63 times 10 to the negative 34 by 3.0 times 10 to the 8th, I'm going to end up with 1.99 times 10 to the negative 25th joule minute, or joule meters. Okay? This is always going to be, I have an arrow pointing to already, why don't I? That's always going to be HC. Okay? So, let's go ahead and apply it to a problem. Okay, so light with a wavelength of 525 nanometers is green, so hey, why not use a green pen, right? And calculate the energy, so calculate E in joules for the green light photon. Okay, so we have the wavelength, we need to calculate energy. So energy is equal to HC over lambda, wavelength. Okay, I know HC is going to be 1.99 times 10 to the negative 25th joules meters. And I'm going to divide that by the wavelength. Now, the thing is, I cannot put 525 because that is in nanometers. Okay, as you can see, this value right here and that unit, this unit and that unit are not the same unit. So this has to be converted over. So let's go ahead and convert it. Right over here, we're going to go 525 nanometers over 1 there is a billion, or 1 times 10 to the 9 nanometers for every 1 meter. Okay, you don't need to worry about your intermediate steps right here. Okay, just solve your equation, but try to keep track of your units. Okay, I have my answer in meters. It'll be 5.25 times 10 to the negative 7 meters. This value is what's going to go there. So let's go ahead and put it there. All right, so now that that meter is there instead of nanometers, now let's get rid of this arrow here. Now my meters can cancel out, and I'm left with just joules. Okay, so if I go ahead and solve this and do the math, I get 1.99 times 10 to the negative 25th divided by 5.25 times 10 to the negative 7. End up with 3.79 times 10 to the negative 19 joules. Now, there's a couple important facts you need to know right here. Okay. Now, I'm only going to give you problems that are going to be involving calculating the energy of visible light. Okay. Well, visible light only takes up so much of the electromagnetic spectrum, which means your answers between the most red and the most violet are going to be somewhere around, the energy-wise, is going to be somewhere around, okay, times 10 to the negative 19 joules. If you ever do a calculation where you end up with like times 10 to the negative 33, you did something wrong. Okay, probably just entered in your calculator wrong. But all of your answers should be something times 10 to the negative 19 joules. If you don't, then you're off. Okay? So let's go ahead and take a look at another problem. All right, so a certain electromagnetic wave has a wavelength of 625 nanometers. What is the energy of that wave? Okay? Remember, the photons are what are moving in waves. So if you say wave or you say photon, it's meaning roughly the same thing. All right, so energy is equal to Planck's constant times the speed of light over lambda. That means it's 1.99 times 10 to the negative 25th, okay, joule meters divided by the wavelength. Again, now the wavelength is in nanometers. We need it to be in meters. If I do my dimensional analysis, I'm going to end up with 6.25 times 10 to the negative 7 meters. Okay, my meters cancel out. I'm left with just joules. So when I do my final answer and I do my final calculation, hopefully we already know that this is visible light. Okay, so it's going to end up with something times 10 to the negative 19 joules, right? The actual value is, let me get a calculator, 3.18 times 10 to the negative 19 joules. Okay, this is really a practice on can you use your calculator in scientific notation calculations. Okay, we're going to do one more. Okay, and I'm going to go ahead and just make one up right now. Let's go with, instead of solving for energy, I want to solve for wavelength. Okay, all right. So calculate the lambda, or the wavelength, okay, of a photon carrying 4.12 times 10 to the negative 19 joules of energy. Okay, so what I'll do first is I need to rearrange my equation. So energy equals hc over lambda, right? Well, I can rewrite this like so. hc energy lambda. And if I want to solve for lambda, I can just block that out, and I end up with hc over E. So I'll rewrite this and go lambda is equal to hc over energy. Okay, so that means I'm going to end up with 1.99 times 10 to the negative 25th joule meters divided by my energy value is 4.12 times 10 to the negative 19 joules. Okay? Remember that 1.99 times 10 to the negative 25, that is the product of Planck's constant times the speed of light. That number will never change. Okay, so I'm going to cancel out joules. I'm going to be left with meters. And if I do that real quick, calculate. Okay, I'm going to end up with 4.83 times 10 to the negative 7 meters. Now that's my wavelength in meters, but I want it to be in nanometers. You're always going to give me your wavelength in nanometers just because I always give you your wavelength in nanometers when you're solving for energy. So if I was to do that, let's go over here, and I'm going to go 4.83 times 10 to the negative 7 meters over 1. Okay, and then I'll go 1 meter is equal to 1 times 10 to the 9th nanometers. When that's just be an N, okay? When I do my math and I cancel out my meters, I am left with nanometers. My final answer is going to be 483 nanometers, okay? A good follow-up question that I will give you, and of course I'll have to give you a reference sheet for this, but instead of just saying calculating the wavelength of a light, I may say, what color is that light? Okay, and if I was to pull up an electromagnetic spectrum, okay, so I'll pull one of those up right now. All right, so I'll pull that bad dog up right here. Okay, here's my visible spectrum. My wavelength was 483 nanometers. So here's 450 in this range. Okay, so 483 would be between 500 and 450. So we're looking at kind of a bluish green. A blue-green color. And that's how you would get that. Okay? And like I said, I'll have one of these available. I'll actually have this exact image available for you, or one similar to it, on the website. So if I did ask you what color a light is based on the energy, then you'd be able to tell me. Okay? If you guys have any questions, please make sure you ask.